Welcome to the second video for the lesson, Powers in the Horizontal Line, Interpreting Parameters in Context. This is under the topic of using exponential equations. In the first video for this lesson, we talked about how we can use graphing technology to assist us in solving exponential equations by graphing either side of the equation on the same coordinate plane. In this video, we're going to talk about how we can create our own exponential growth or decay equations based on a particular scenario. So let's start by talking about Simone. Simone has invested $500 in a mutual fund, which has shown an annual increase of about 10%. That word increase is letting me know that we are talking about exponential growth. So I'm going to go ahead and write down my equation, and I'm going to use f of t because we're talking about a function of time when we're talking about these accounts year over year. That is equal to p, which is our principal or initial amount, times the quantity 1 plus r, I'm adding because this is exponential growth, to the power of t. So substituting in the information that I've been given here, f of t equals my principal starting amount, which is $500. So 500 times the quantity of 1 plus r, that's my rate as a decimal. So that would be 1/10 to the power of t. I can add here inside of my parentheses 1 plus 1/10. So my final function here would be f of t equals 500 times 1 1/10 to the power of t. Now let's see if we can read a scenario and match that scenario to a specific function. So here we're talking about the population of a city, which starts at 42,500. So since that's the initial value that I'm given, that's going to be my p value or my a value if we're thinking of it in terms of the general structure of an exponential function. By 2010, the population had grown to approximately 51,708 people. That word grown is again giving me the clue that this is going to be exponential growth. So just by looking at the initial population of 42,500, that is my original value. So my a value, if we're thinking about the general structure, and I'm going to make a note of that general structure here on the side, f of x equals a times b to the power of x. So that's one way that we could think of this here. We're also talking about exponential growth. So we're talking about p times the quantity of 1 plus r to the power of t. Now, remember, for exponential growth, we know that what's inside of our parentheses here, which is equivalent to our b value, has to be greater than 1. So just knowing that information, that the b value has to be greater than 1, there are some answer choices here that I can certainly eliminate. For example, here we have a b value of 0.96 because that's less than 1, that represents decay. There's no way that can be the answer. For the same reason, for this option here, there's no way that can be our answer either. Now let's talk about the initial value, so that a value. We know from the scenario here that my a value should be 42,500. So that means I can eliminate this answer choice because the initial value is not 51,708. That's the ending value. And for the same reason, I can eliminate this answer here. Now with my final two choices, I'm noticing at the exponent on this option is 5 times t, which is not accurate. We would have to substitute a 5 in for t if we wanted to actually solve this equation, because from 2005 to 2010 is 5 years. Our beginning time is 2005, but it's not going to be 5 multiplied by t as is being showed in this option. So that is not it either. That means that f of t equals 42,500 times 1 400ths to the power of t would be our correct answer. Thank you so much for watching.